Hey guys, your boy Chili here. Welcome back to Hardware 3D. Today's topic is going to be the implementation of shadow mapping. In the previous video, we covered the theory, the algorithm that goes into it. So if you have missed the previous video, it's called Shadow Mapping Theory. I highly suggest you check it out before watching this one. This one, we're just going to be focusing on the code, the actual implementation here. So let's jump into said code, shall we? First commit here, we are creating the ability to basically bind a camera to a point light, because as you should already know, it's very important to be able to render from the point of view of the light when you want to do shadow mapping. So in pointLight.h, we add shared pointer to a camera, and what we're going to do is when we create a point light, we're going to create a camera for that light. And then here, when we change the position of that point light, via our ImGUI control window, we also want the camera to move to that same point. So we want to tether the camera to the point light. So whenever any of those X, Y, or Z change for the point light, we are going to call set pause on the camera. Now looking at camera.h, we notice it did not have a set pause function. The only way to set the position of the camera originally was through the ImGUI interface. So now we want to be able to programmatically set that position. So we add this function set pause. We're also going to add a flag to cameras, whether or not they are tethered. So, the camera for the point light is tethered to that point light. And that's important because we don't want, we also have ImGUI control for our camera, right? But we don't want to be able to move the camera independently of the light. So if the camera is tethered to the light, we want to disable those controls. And that's what we're doing here, right? We check if we're not tethered, then we render the controls for X, Y, Z. Otherwise, we disable the ability to move the camera. Any camera container, we're just going to change from using unique pointer to shared pointer. Because obviously now we want to share pointers. We want to share access to the camera between our camera container and between the point light for those cameras that are tethered to point lights. At the top level, there's only one small change here. We add a third camera to our container of cameras, and that's the one that we share out of the point light. So when we do this, right away, you can see, we've got a camera, and it is coming out of our point light here. If we make this light camera the active one, we can see the scene we're seeing is what we would expect based on this visualization here. And we can control that light camera. Notice that when I changed here, we lost the position controls because they're not enabled for cameras that are tethered to point lights. But we can change the orientation here. And if we change the position of the light, then we see that the camera moves with it. All right, so the next commit here is called saving depth. What are we doing here? Well, the first thing I wanted to be able to do is just be able to store a depth buffer as an image file for, debugging, just to see it, just for the video's purposes. So create a function, store depth in the render graph. Well, actually, let's take a look at depth stencil. So we added a whole bunch of functions in here. The main one for storing is it's going to be the same story as we had for render targets, right? We want a function that'll convert this depth buffer to a surface, and then we can call save on that surface, store it as a file. Now the other thing we're doing here is we're preparing the depth stencil for the ability to bind it as a texture, as an input. And this is a little trickier than for render targets. It was very simple for render targets because render targets store data in the same way as a texture does, RGB data. But depth stencils store depth, and that's treated differently in Direct3D. So how does this pan out? The basic problem that you're going to run into when you try to do this for yourself is that when you want to bind depth stencil as a depth buffer, Direct3D expects a format like this. With D. It wants the D is basically what I'm trying to say. It's thirsty for the D, and that makes sense. If it's depth, it's going to want a depth channel. So D24 or D32. But if you try to bind a DXGI format with D in it, you try to bind that as a texture to a pixel shader, you're going to get some fat problems. You're going to get some errors, and it's not going to be a good time. So what the texture input wants is it wants RGB stuff, at least an R, possibly a B and a G. But I mean, what we're doing right now, when we create the underlying texture, the actual resource, we're creating it as a D type. And then down here, when we create the actual view on that texture, the depth stencil view, we're creating it, basically, we're just telling it, yeah, just use the same format that is the actual format of the texture. So what we have to do, if we want to be able to bind both as a depth stencil and as a shader input, is we have to create the texture with a typeless format. So we do format, R24, G8, typeless. So we're not saying, even though it says RNG, we're not actually saying whether this is color data or whether this is depth data. We're just saying there's a 24-bit element or component and there's an 8-bit component, but we're not telling you the types of them. And here we're saying there's a 32-bit component, but again, I'm not telling you the type. So we create a texture with a typeless format. And then when we create the view of that as a depth stencil view, then we tell it, okay, you were going to view that, you're going to interpret that as D24 S8, or you're going to interpret that as a D32 float. On the other hand, when we're creating the shader resource view, that's the view that we use to bind something as an input, then we're going to say, no, you want to interpret this as R24, and the other 8 bits are just typeless, forget about them. So you're going to interpret the first 24 bits as color, or on the other one, you're going to interpret the first 32 bits as a floating point color. So the basic idea is, again, you create the texture with a typeless format, and then when you create the views, you choose the view that's most appropriate for the thing that you're doing. So that's the major part of, this code here, what I'm doing. It's just selecting the correct format based on, what we're doing. We're creating the underlying resource, or we're creating a view on it as depth, or we're creating a view on it as color. Now, the other thing I'm doing here is I have added 2 distinct usages for my depth stencil. One is as a depth stencil with depth and stencil parts, and the other one is as shadow depth. So for shadow buffer, we don't need stenciling. So it's a waste to have those 8 bits in there doing nothing. So for shadow depth, we are going to actually store the depth data as a 32-bit float. We use the full 32 bits, and that's a good thing to be able to do. What these functions in here are doing is they're just creating us a way of mapping based on, what the type of thing we're creating, whether we're creating, a view or the underlying texture, and depending on what our current usage is. So it takes all that information into account, and it maps us out at the DXGI format that we need. And again, the second part of this, the part that was actually in the name of the commit, is the ability to convert depth stencil buffer to a surface so that we can save it. And this is pretty similar to what you saw, what I did for render target. If you're unclear on this stuff, you can go back to my video where I talk about the conversion from render target to surface. I just mostly just copy and pasted that code into here anyways. So yeah, next, what are we going to do? We create the surface based on the width and the height of our render target, or of our depth stencil. We map into our staging texture. We get pointers that we can access from the CPU side. And then we're just going to copy the data. Now this next part here is similar to what we did for the render target, but there are some differences because the data is different, right? So again, we have a loop in the Y and then a loop in the X. That part's the same. But the actual data type of each one of those individual pixels is a little tricky, right? Because we don't know what it is. It could be 24 bits, or it could be a 32-bit floating point value. So what we're going to do is first, we just create this placeholder data type called pixel. It's just 32 bits. That's all it is. And we're going to use that to do our pointer arithmetic. So we're going to cast, well, first we get our pointer into the start of the current row. So we multiply the row pitch times the current row that we're on. We add that to the pointer to the beginning of our buffer here. Convert that to a pixel. Then when we are looping horizontally through that data, how we interpret that data is going to depend on the format that we're actually working with. So we look at the texture desk and we have the format in there, and we got to check to see if it's a 24-bit type or 32-bit type for that first one. And if it's 24-bit, then we know it is a U norm. So normalized data there. So what we're going to do is we're going to mask out those last 8 bits like this, and we're going to interpret this thing here just as an unsigned int. Mask those out. Now we have a 24-bit unsigned integer value. Now we want to divide that so that it's going to be a value in the range of, 0 to FF, 0 to 255, because color channels, they range from 0 to 255, right? It's easy. We just shift right by 16, and that divides by the amount that we need. Basically, it just cuts off these lower bit values that aren't going to be important. It just takes the most significant bits, and that is going to be what dictates the value of the channel. And then we just copy that into RGB. So we duplicate this single depth into RGB. That gives us a grayscale value between 0 grayscale and 255 grayscale. On the other hand, if we're dealing with a 32-bit float, we're going to, just reinterpret that as a pointer to float here. Then we're going to multiply by 255, because it's going to be value 1 is full color, 0 is no color. So we're going to scale that up 255 and then convert that to a car value. And again, do the same, duplicate those channels. And that's it, you're done. Once you've looped through all the pixels, you will unmap that texture, and then you return your filled surface. And then in app.h, it's very simple. I create a flag here, saving depth. And then if I press the return key, it sets that flag. That flag is checked at the end of rendering here. And if it is set, it is going to call store depth on the render graph to a file called depth.png, and is going to clear that flag. And in the render graph here, store depth, it just master depth, convert to surface, save. That's it. Very simple. All right, so in our standard scene here, I'm going to press enter. That should have saved a file. And if I look down here, yes, I have depth.png. Let's open it up, and here is our depth. Now, you're looking at this and saying, Chile, that's really washed out. I mean, I can't even see the nanosuit, bro. You can't even see him. It's so washed out. And the reason for this is that because of that, the perspective divide and the mapping that we do, all the precision is really very close to the camera, and everything far away is pretty much just very close to the same value. And that's mostly just a property, of the Z divide that we do. So if we want to correct that, probably what you want to do is just do the reciprocal of the current value that we're storing for depth. And that is going to correct things. Only our depth values are mapped from 0 to 1. So if you do the reciprocal of that, 0, which is the closest value, is going to map to infinity depth, and 1, which is the furthest away, is going to map to 1. But we don't want that. For the most part, we still want to map 0 to 1, so that 0 should map to 0, and 1 should map to 1, but the mapping should be linear. So how do we do that? Well, let's call it D. D for depth. Okay. So what we have is 1 over D, and that's no good for a number of reasons. What if we tried 1 over 1 minus D? That's a little better, right? Because that means that 0, the closest value, is going to map to 1. And then 1 is going to map to infinity, right? So now we have an increasing scale. It's a scale that increases to infinity, which is bad, but it's increasing. Now, what if we do this? So instead of 1 over 1 minus D, we do 0.01 over 1.01 minus D. So what do these map to? So D equals 0 is going to map to 0.01 over 1.01, which is about 0.01, which is pretty close to 0. So 0 is going to map to a value that's pretty close to 0. And 1, that's just going to map to 1, right? Because 1.01 minus 1 is 0.01. 0.01 divided by 0.01 is 1. So now we have a mapping that maps from basically very close to 0 to 1. And it does it linearly because we're taking the inverse. And that is what I use. Now, this isn't a perfect inverse mapping of the transform that we did. At the time I was coding this, I couldn't be fucked to actually do the exact mapping. And it doesn't matter. All we're doing is we're converting this for visualization purposes. If you want the exact mapping to cover the proper world space Z value, you'd have to take into account the near plane and the far plane and, do a bunch of math with that. But I was like, hey, you know what? I don't care. This is just for visualization. So I didn't do it. I just used my intuition and I said, well, we have to inverse it. So let's figure out an inverse that maps it to basically the range of values that makes sense. And that's what I did. So we look at linearizing depth on save. I had the ability bool flag here to say whether you want to linearize it or not when you convert to a surface. And then down here, the original casting of the raw value is the same. Then if we're linearizing for the 24-bit thing, first we normalize by dividing by the float equivalent of OX FFFFFF. So that'll give us a value between 1 and 0 floating point. And then we do that algorithm that I showed you. 0.01 divided by 1.01 minus the normalized value. That's it. And the one down here, it's the same idea basically, except that we don't have to do that normalization, but it's the same in the end. And if we look at the depth captured from the exact same perspective, only with the values linearized, we now see something that, makes a lot more sense to us. We can gain a lot more information from this than we could from the previous capture. All right, moving on. So in the previous video, I talked about the idea that we're going to have to render now from different perspectives. And not all of those perspectives are going to be going over the same geometry. So we can't just render through one pass through the scene graph now. We're going to do multiple passes through the scene graph that touch different things. And not all of those passes are going to want to render the same effects. So what we have to do is we have to have channels that say, okay, this pass through the scene graph, this one is only going to be dealing with shadow mapping, and then the other pass is going to be dealing with the other effects and not dealing with shadow mapping. So, and the way to do that is actually pretty simple. It hinges on two things. First off, every technique is going to store the channels on which it is active. We're going to store those channels just as a bit mask, as a 64-bit bit mask. And then whenever we call submit on a technique, we're going to pass in the channels that we're currently broadcasting to. So every submit is going to specify what channels it broadcasts to. And when that submit reaches the technique, all you're going to do is AND the broadcast channels, which I call in here channel filter, with the channels that this technique is actually active on. And if that result is non-zero, then the technique is active and we can submit to its steps. That means that everything that submits has to take in and pass on these channels. So for example, drawable, submit now takes in a channel filter. Or let's say mesh. Yeah, mesh for mesh, submit now takes in the channels that we are broadcasting to. I create a little header file here called channels, and it just has a bunch of constants here for the channels. So there's a main channel right now and a shadow channel. If we look at material now, when we create a technique, we also pass in the channel or channels that it is active on. You can or them together. You can create, put multiple bits in the channel mask. Generally, you're going to have, one technique is active on one channel. So we see here the Fong technique is active on the main channel. The outline technique also active on the main channel. All right, next commit here, pretty big one, bind camera to render graph. Up until now, we've just had a single camera. It's been bound to graphics globally. And once it's bound to graphics, it's all done. All the rendering is done using that camera. Now we're rendering from multiple points of view in a single frame. We can't just bind to one global thing in the graphics. The render graph has to be aware of different cameras so we can associate different cameras with different passes. So in rendergraph.h here, I add a couple functions, bind main camera and bind shadow camera. And I don't think I implement bind shadow camera yet, but for bind main camera, we find pass by name, and then we call bind main camera on that pass. So this enables the outside world, the user of the render graph, to associate a specific camera with this camera is the main camera used to render the actual output scene. And this requires a few things. We have to be able to find a pass by name, and the Lambertian pass needs the ability to bind the main camera to it. So find pass by name is going to be added to the root render graph, the very base class. You give it the name of a pass, it returns a reference to that pass. And then in Lambertian pass, we have the function bind main camera, which just sets a pointer to whatever was, passed in there. And then when we execute this pass, we are going to bind that camera to graphics. So instead of binding a camera to graphics outside of the render graph, we now give the render graph agency and allow it to determine what cameras are bound at what time. Camera container, we just give a function to get a reference to the active camera. And then in app.cpp, instead of binding the camera to graphics directly, we call bind main camera, and we pass it the reference to the active camera. All right, in the next commit here, we're actually going to add a pass to our render graph to render the shadow map. And we're also going to have the ability to dump that shadow map. So moving forward, again, obviously we're going to add that pass in here in our blur outline render graph. We're not connecting it to the Lambertian just yet. We're only generating the shadow map, but nothing is actually using it yet. In material.cpp, now for our material, we're adding another technique, the shadow map technique. And this one's different than the other ones in that it doesn't need a pixel shader. It just needs the input layout for the thing that is being drawn and the transform cbuff to handle the transformations. You might say, well, where's the vertex shader? Well, I mean, everything is going to have the same vertex shader. That won't change for shadow mapping. And so we pull that up into the actual pass itself. So the pass contains the vertex shader, which is just a solid vertex shader, null pixel shader, stenciling off, blending off, Bob's your uncle. We're going to set the depth stencil for this pass to be a shader input depth stencil. And the usage is going to be shadow depth. And we're also going to register that depth stencil as a source for, subsequent passes to be able to link into, although they're not doing that just yet. We also add a little function here, dump shadow map, which will be useful for this commit for the testing that we do. And it's very simple, convert to surface and save. We also give the test cube. We also give it a technique for shadow mapping, since it's also can cast shadows in the scene, and it's not part of our mesh system. It's its own independent drawable type. But yeah, we do that. Then in app.cpp, instead of dumping the depth from our normal render, we are dumping now the depth, saving depth from the shadow map. All right, so it'd be pretty boring to dump the depth from this view right here. So let's make the light point at something a little more interesting. That looks good. All right, so if I press enter, it should dump the depth. And if we look at shadow.png, yes, that does look like what we would expect from that. So now we have a separate rendering pass that's only rendering depth values, and it's rendering them from the point of view of our light source. Now there's one more thing that we need to provide to our Lambertian pixel shader. Besides the depth map, which we now are able to provide, we also have to provide the transform of the camera that was used to render that depth map, so that we can transform from world space or whatever into the light space to compare with the depth map. So for this purpose, I create a bindable, call it the shadow camera cbuff. And it's different than the transform cbuff. The transform cbuff maintains a pointer to its parent, and it uses that to get the transform information. In this one, we don't need that. All we need to do is set the camera that this shadow camera cbuff is hooking into, and then it can get transformation information out of that camera. But otherwise, it's fairly similar. We have a matrix here. That's the view projection. When we want to update that, we get the view matrix and the projection out of the camera, multiply them out, transpose them, and then update the actual underlying constant buffer. Bind is just called bind. Then in our Lambertian pass, we are going to store a shared pointer for a shadow camera CBuff. Also a shared pointer for the shadow map that's going to be linked to the shadow mapping pass. So you see here, we register shadow map as a sync to be connected to the source of the shadow mapping pass. And we add the shadow CBuff just to our list of bindables here. And now when we're executing our Lambertian pass, we are going to update the shadow CBuff. That is going to grab the new transforms from the camera. Camera just needs a function to get the projection. No big deal there. And now here, for our Lambertian pass, we set the linkage. Shadow map is going to be linked to our shadow map pass.map. Oh yeah, and I also added the function to bind the shadow camera, and that just sets the camera of the shadow CBuff. So yeah, now everything is linked in. The Lambertian now has access to the shadow map and the shadow transform. So the stage should be set now for us to actually write the shader for the shadow effect. As you can see by the name of this commit, things did not go 100% as planned. But first, let's take a look at the actual implementation of the shadow mapping effect before we start to talk about the problems that we encountered. So in the Lambertian pass here, we wanted a sampler to be used for sampling the shadow map. So we actually create a new bindable here, shadow sampler, and it sets the sampler state for sampling our depth map. And this is important here. We're using a border type texture addressing. So you should be familiar with a few texture addressing modes by now already. For example, if this is your texture space and you try to texture at the coordinate here, if it were a wrapping texture, it would probably try to go from here. Or if it were mirror or reflect, I forget what it's called, then it should try to sample from here. If it's clamping, it should try to sample from here. What we have is border. So what border does is if you try to sample outside of the 0 to 1 range of the texture, it just will return a constant color. So everything outside of this is just decided to be some kind of constant color. And that's useful for our current system of shadow mapping, because if we try to sample the shadow map outside of the region that we rendered it from, I would just like to be able to disable shadow mapping altogether. And this will let us do that. It'll just return a constant value, which we could set to be, the furthest depth possible. And so then that would make the scene work properly. It's not a huge deal in the big scheme of things, because later on we're going to get full coverage. But for right now, it's useful just to be able to specify what happens when we try to sample outside of our shadow map. So what we're doing is we're setting the border color, the first component, to be 1. We only need the first component, the depth component. So we set it to be 1. That's the furthest depth possible, and that'll help us out. So what I've done for this simple test here is in material, I've basically commented out shadow mapping technique. And so all I do is I just want to narrow things down, only generate shadow map for our test cube. And I'm not going to use the Phong shader or anything. I'm just going to create a shadow test shader, shadow test vertex shader, shadow test pixel shader. So the vertex shader is our basic vertex shader. Only we're adding one more thing into here. We're adding this matrix shadow view. So what we're going to do is instead of mapping from world space or whatever into the light space in the pixel shader, we can do most of that work in the vertex shader. So we add an additional member in here, the shadow camera position. So we take the position of the vertex in object space, we multiply it by the model transform, that brings it into world space. Then we multiply by the shadow view, which contains the view and the projection of the shadow map. And that gives us the coordinates of this vertex in the homogeneous space of the light. These names are a little messed up. This shadow camera doesn't really make sense here. This is the world position of the vertex, and this is the position of the vertex in homogeneous space with respect to the shadow camera, or with respect to the light, if you like. All right. Now, there's one more thing that we can do in here, because you have to transform from homogeneous space. Well, you have to do the depth divide, and then you have to transform from NDC coordinates into texture coordinates. So to get into texture coordinates from NDC, basically you multiply by 0.5 in the X, you multiply by negative 0.5 in the Y because you have to flip the Y direction. And then you have to add 0.5 in here, and that'll bring you from negative 0.5, positive 0.5 into 0 to 1 range. Now there's only one little trick here. The actual division, the depth division, has to happen in the pixel shader. So what you end up doing here is, if you just did it like this term here, this constant term, this additive term, would get divided by depth and it would be wrong. Because this addition has to happen after the depth division. So what you do is you pre-multiply it by W. And then when you divide W, they cancel out, and it'll just be the same as adding in this offset after you've done the depth divide. So if we do this, we can get a little bit of extra work done in the vertex shader. Then in the pixel shader, we're going to have this shadow position, and this is texture coordinate, except it needs to be divided by depth. If you divide this value by depth, you will get the texture, the lookup into the depth texture. So first of all, for the shadow test pixel shader, we need shadow map, and we need the shadow sampler. Now what we're going to do is, before we do any rendering in here, we're going to do a very simple test. First of all, we're going to divide by W. We're going to divide X, Y, Z by W, do the depth division. This will give us our X and our Y in texture space for the depth map. And the Z will be the same Z as you find in the depth map. It'll have the same transformations applied to it, so it'll be comparable to the depth value that you see in the depth map. And then all we're going to do is sample our shadow map with that XY texture coordinate. We're going to get the R out of it, which is the depth, and we're going to compare that depth out of the shadow map with the depth that we got by actually transforming the vertex that we're looking at. So if the depth in the shadow map is greater than the depth that we're looking at, that means that this thing that we're looking at is closer, the same distance or closer, and therefore we should perform our lighting calculations. Otherwise, what we're going to do is we're going to set diffuse and specular to 0. We're not getting any light from our light source. The only light we should have is just the ambient light. Now, the only other major change in here is the transform here that I'm passing in. I also now need the model matrix. Model view projection, but also just the model. The reason for that is because to do the light space transformation, we got to go from object space into model space, then from model space into the homogeneous space of the light. So we need extra matrix there, which means, extra matrix here, and transform CBuff has to pass in now model view, and model view projection. I mean, there's tons of different ways that you could to organize this. This is the way that I went with. It's not a big deal. So this is great. We got this thing now. Only one problem, it doesn't work, obviously. I mean, obviously we should be seeing some Mondo shadows being cast by this cube here. Not seeing any shadows being cast. So to fix the problem, Chili puts on his debugging hat. He runs through the program with the graphics debugger. And long story short, I figured out that, yeah, my shadow map wasn't actually being bound to the pixel shader. I was like, well, no, it's right here. But I had just copy and pasted from this stuff in here. The register sync, direct buffer sync, render target, depth stencil. The problem is this bindable here, you can't just register sync like this. Like I can register it as a sync, and then the render graph system will link up the output from the shadow mapping pass into this bindable. But when we call execute, it's not actually going to bind it to the pipeline when we're rendering, so it doesn't get bound. It exists, it's linked up, but it's not being bound. And there's two ways you could do this. If you wanted to use register sync, you would have to manually bind here. So you'd keep this shared pointer, you would manually call bind on it in the execute function. But a better way to do it is to add bind sync. So what we're doing is we're adding it to the container of bindables and also exposing it as a sync. Doing both of those at once. And if it's in the container of bindables, we don't need this separate pointer here, and we don't need to manually call bind. That happens automatically in the machinery of a render queue pass. And if we do that, here is what we get. You might say, I don't see the shadow chili. Where's freaking shadow? Well, for the testing purposes, the only things that can cast shadows and the only things that can receive shadows at the current point is the test cubes. So with that in mind, we can see that this test cube behind here, it's working, right? This is what you would expect. The front face here is facing the light source, but it's not being lit because this one in front of it is blocking the light. So that's good. Let's look at the one in front now. Oh my God, look at her butt. This is pretty messed up, ain't it? So it's starting to work. You can see it's working very nicely here. Here, not so much. What gives? What's going on here? Well, that's the story for another video. You know Chili got to hit you with the cliffhanger there. So, in the next video, we're going to figure out what this problem is. We're going to figure out how to solve it. We're also going to bring shadow greatness to the rest of our scene here, not just the testing. So we're gonna have to overhaul all of our shaders now, all of our different types of shaders to handle shadowing. And I don't know, we might also look into some technology to make the shadows look sexier. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.